Hello, good morning or good afternoon, wherever you may be. This is Prakash Khanduri from Ambiq. I'll be walking you through a wearables audio system design fundamentals. The topic for today presentations are, I will walk you through briefly telco history, then transducers and acoustics we need for designing any telephone system. Auditory systems, Cochleae models, speech productions, and how machine understands human speech. As part of this session, we'll briefly describe these things because we'll be using these concepts when we'll be discussing about the signal processing aspect, what kind of auditory transform we need, and how we design various algorithms. So these concepts will come handy at that time. We'll wrap up describing what kind of instrumentation one will need for characterizing acoustics and algorithms, or even tuning the system. So this is a brief history of various telco endpoints. Started way back in 1876 when Graham Bell invented a patent in 1875. And in the following years, they were able to basically put the system together and build a first commercialized phone, although they were talking between the two rooms. But that was a fundamental concept used, and later on it was used for PSTN network. Since then, there has been a lot of innovations. And in 1932, Bell Labs invented a rotary phone, followed by 1963, a DTMF phone. Motorola in 1983 built a very first commercial cellular phone, although the concept of cellular phone was proposed by Bell Labs 1957. And in 1978, they demonstrated that how the network can be used for cellular communication. Since then, there has been a lot of innovations in network protocols, communication technology, digital signal processing, wireless technology. All these things were coming together. What we see today on our smartphone because of all these innovations. In 1993, Motorola proposed or demonstrated the concept of a smartphone. Then BlackBerry, back then it was RIM. They were pretty popular on a business systems, and all the B2B customers were using a RIM device. I mean, in between there were pagers where you can send just SMS, but through a smartphone, RIM and Palm, Trio, they were pretty popular for some time. The real revolution took place when Steve Jobs in 2006-7 demonstrated a smartphone with the ecosystem, how you can use app to reconfigure your or repurpose your smartphone. And that was a complete transformation of modern telco system. However, they did not stop there. I mean, the researchers did not stop there and started saying that now, do I really need a big, bulky smartphone? Can I use a wearable form factor, which is with me all the time? And wearables going forward will be the most popular for many other applications, healthcare, secure access, and telco. So recently, including us, has been packaging or defining or innovating these power efficient SoCs that can power these wearable devices in cost effective and power efficient way. We believe the future telco will be some form of wearable form factor. It will not replace the smartphone or computer, but it will be the endpoint of choice from telco point of view. Example, AI is helping. One of the reasons that a smartphone become popular, you can send text messages, you can email, and you are basically always connected. Same can be done through the wearables. Now, instead of a keypad, you will use your voice command, and voice command can send an email, can send a text, and vice versa. On the receiving side, text to speech. So there will be one way or other way, wearables play a significant role on telco ecosystem. That's about the endpoints. Now let me give you a brief history on the network side and on the speech coding side. So let me start with the network on the right side. First PSTN network was commercialized in 1877. The very first commercial 1G phone, it started in 80s when Motorola in 1983 built the very first cell phone. And since then, there has been innovation going on the network protocols, 1G, 2G, 3G, 4G, 5G, and we are now talking also 6G. So how do we increase the data rate? And that's what basically this wireless generation means. Up until 2000, when 3G was getting deployed, and landline, they completely changed their communication, the telco, and instead of using a PSTN based, we started using an IP packet for sending voice. And at that time, the standard was known as a VoIP. The speech coder used for VoIP were G711 and G729, whereas for cellular, MR narrowband, and there were some other speech coders, but I'm not going onto them. Up until 2010, there were two different telco standards, the landline and the cellular. Basically, landline was using both PSTN as well as VoIP. And on the cellular side, we were still using a circuit switch connection. In 2010, when LT was deployed and first time IP protocols were used for data transmission on the basically 4G network is a data network as opposed to circuit switch based. And a new concept that let's use IP telephony standard, put it that back on the cellular. And we started calling that a VoLTE, voice over LT. It uses the same SIP signaling protocol and RTP for sending a media protocols. And now in the 5G, again, we using the same protocol. It's basically IP-based communication protocol. Just new name is voice over NR because it's a new radio. In the air interface, it reduces latency by 10 millisecond, which means you will have a better quality. In terms of the speech coder from MR narrowband, VoLTE uses MR wideband, and one of the reasons for when they convinced the consumers why you should be switching to VoLTE, because people were really used to with their 2G phones, and they said HD voice has a best quality, and that was the key selling point why people switched from landline to 4G VoLTE devices. So that's basically a brief history on. Once the 5G came, instead of using separate speech coders for voice and audio coders for music, people start thinking, can I use the same speech coders for both music and voice? And that's where the EVS on a cellular side, which is basically a super wideband, where you can send both music and voice on the same, use the same coders. And on BLE LC3, which uses pretty much same coding rates. Most recently, there has been LC3 Plus, which uses 96 kilobits per second data rate, and will be used for most of the smart home devices for streaming. So that's a very brief history of telco system. With that, we can now come back to what we need to know in order to design a telephone. So the first thing we want to discuss here is the transducers and acoustics. Voice coil-based loudspeaker has been widely used in telco endpoints, whether it's a conferencing system, professional audio, smartphone, smartwatch, or even headsets. One of the limitations of the voice coil-based is A, it consumes power, and it requires a magnet, which means these are bulky. On a wearable form factor, specifically for a smartwatch, to generate a loud sound, we need either a larger loudspeaker or a deep cavity. We don't have that both in terms of the space and in terms of the cost and power. Most recently, there has been a research on utilizing MEMS-based loudspeakers. And there are many companies, but I am only listing 3 of them here: Sonic S, XMEMS, and USound. And they all are claiming that these MEMS speakers, which are basically anti piezoelectric effect based. It means if you, in some crystals or some piezoelectric material, they have a property. The input voltage can deflect these piezoelectric crystals, and with a carefully designed cavity, you can convert these deflection into acoustic waves. Since these are semiconductor devices, we can produce them in larger scale. Based on the data sheets from these manufacturers, they outperform in terms of the power consumptions and size, voice coil-based systems. For example, if we take 8 ohm or 4 ohm voice coil and compare that with the MEMS-based loudspeaker, its size is 1/10, power consumption is also 10 times less than what you will have from the voice coil. They are very linear, specifically Sonic Edge, which uses basically this ultrasonic pump, and they are claiming that you can have at low frequencies automatically boost and also at high frequency automatically boost. And when we will be talking about equal loudness curve, or which frequencies are responsible for loudness and intelligibility, turn out to be that the MEMS speaker has greater potential in terms of the cost, in terms of the performance and power consumption. So how speakers are characterized? The first thing we look on is its frequency response. Standard specifies for a particular mode or for particular applications or use case, what shall be the frequency mask. And here is an example. For typical hi-fi system, we will need to go down to 100 hertz or even 50 hertz. If you take loudspeaker, it has a very poor performance if you just measure it in the free space. By putting a cavity around, its performance increases drastically. So if you are designing a speaker system for home, you have a choice of selecting where you want to place the speaker, what should be the size and all that. In a wearable form factor, we are limited by the space. Therefore, manufacturer need to, in wearable form factor, we cannot, in wearable form factor, we are limited by size and power consumptions. We cannot have a deep cavity. By the way, for most of the telephone, people use bass reflex baffle. And there is a leak port or tune port, which gets calibrated based on where you want to get this F0, means a 3 dB cutoff in terms of the frequency response. So in order to get the lower and lower frequency response, acoustic need to be designed that way. When we will be talking about dynamic high pass or DRC or equalizer, we'll come back to this graph later on. But just to give, to say here that, or to show that lower frequencies are hard to generate from these small form factor devices. So again, this is a typical frequency response for hi-fi. We take a wearables, because of the small size, you cannot really get the loudness you need. So primarily, we are limited by the low frequency these acoustics can generate. They can vary anywhere from 500 to even sometimes 1000 hertz, depending on what kind of loudspeaker and acoustic they have selected. We take a frequency response of a hearable device, because hearable devices are sitting close to our ERP. They can generate loudness, and we can get a desired frequency response without much distortion. So the typical impedance for, if we use a voice coil for hearable, is 16 or 32 ohms, for wearable 8 or 4 ohms load. So this is basically a frequency response. It comes straight from the standard. Standard provides the lower mask and upper mask. And in terms of meeting these requirements, standard specify that how the frequency response should look like, what should be the loudness, what should be the distortion, and all these are. So what we are describing here is basically giving you a brief intro on what we need to take into considerations when you are designing a telco device. So that was about just a loudspeaker. Now, what kind of amplifier you will select? There are 3 types of amplifier. Class A amplifier, they They are a choice of amplifier for professional audio, but for telco, specifically on wearable form factor, they are not suitable. Primarily, their efficiency is only 25%, which means 75% goes in heat dissipation. In battery-operated devices, that's no. Another type of amplifier, and these are, by the way, the most widely used in cellular devices. These are Class AB amplifier, and they are 60% efficient. There is another flavor of how we are controlling the rail or the power on these Class AB. It's called Class G and H, and they provide efficiency up to 90%. In order to select the amplifier for hearables, you will need about 100 milliwatt. And the gain that can offer you, it's an attenuation basically, 0 to minus 24 dB. And we'll come back on that, what that meant. There is a third category specifically for devices that need to generate more power. Class D amplifiers are widely used. They can offer more than 80% efficiency. They can provide some gain also, and they are most widely used for hands-free devices, home entertainment, smart speaker, smartwatches, and smartphones. How you will characterize acoustics? One way to look on is plotting frequency response versus distortion. And to see that, how well your acoustic is behaving, you have given a requirement for meeting certain frequencies, lower frequency characteristics. So one way to do that is you will need to take a distortion TSD versus sweeping a frequency and then plot it. And that will tell you how well your acoustic is behaving. This curve will come handy when you will be tuning the system. How I should be applying a DRC, what kind of a high pass I need to do. So this is extremely important to understand, and sometimes based on my own experience, you wanted to measure this one when you are using a pure acoustics, not including signal processing. So this will give you an indication how well your acoustic is designed. What kind of a sampling rate your front end need to support in the playback path, 8 kilohertz to 48 kilohertz, and bit width 16 to 32 bit width. For wearable form factors, of course, if it's a headset, then definitely more bit width and sampling rate will give you much clearer sound quality. However, these are battery operated devices. We are limited by the battery power. We are limited by the memory. Therefore, the care has to be taken what operating mode you should operate these, bit width and sampling rate. So this is a gray area. Default, it will be 16K sampling rate, 16 bit width for telco. That was about the loudspeaker. Coming to the microphone. Microphone is a transducer that converts your speech into electrical signal. And there are two types of microphone, electret and MEMS based. MEMS microphone can be both analog or digital, but we will primarily say about digital here. Electret microphone, it's polymer based. It's a capacitive transducers, and it converts sound wave into electrical energy. It's determined by the sensitivity of the microphone. It means to take a defined input sound pressure level, what output voltage it generates. And the sensitivity is determined by is specified around minus 38 to 46 dBV. What else you will need along with that? Clock, biasing circuitry, you will need a low noise programmable gain amplifier. 24 dB is a typical minimum you will need when you are selecting. Some customer may be asking for more, specifically for some specific healthcare applications. Sampling rate requirement says 8 to 48 if you want to support EVS. Bit width 16 to 32 bit width. DRC, again, dynamic range from 120 to 110. And we will come back on this one when we'll be describing about the auditory system dynamic range. Digital mic versus analog mic. When you will use digital mic, when you will use analog mic. Analog mic provides a better performance in terms of the power. They are very linear from low frequency to the high frequencies. Our analog mic needs a special care when you are designing acoustics. Digital mic, these are MEMS-based microphone. They are already on a chip, so You don't need to care about that much in terms of the acoustic. You can solder them in a PCB directly. You will need a clock, which is usually from 1 to 6 megahertz, depending on the microphone you select. It comes in a pair. At rising edge, you can get data from left mic. On the falling edge, you can get data from the second mic. You will need a special circuitry for driving these digital mic, PDM circuitry, and rest requirements are the same. So to characterize the microphone, sensitivity is one parameter for analog mic, minus 38 to 46 dB. Again, the data sheet specifies how much is that. For MEMS, it's minus 26 dB. The frequency response, which is basically the magnitude versus frequency, and the directional pattern means there are three types of beam pattern: omni mic, bidirectional mic, and directional mic. And depending on your applications, you will need to select the type of microphones. Of course, directional microphones are expensive. So again, it depends on all your applications, what kind of microphone type you need. Here is a frequency mask for a typical microphone. This is a lower frequency mask, and this is higher frequency mask. And this is basically an actual measured curve. There is an important, it's usually known as a orthotelephonic response, and it is defined as the following. If two people are sitting and talking in a free space, 1 meter apart, and then we measure a transfer function at ARP. ARP is an air reference point. If you take your thumb, put it in the ear, and this distance inside, it's called an air reference point. And then when we measure the transfer function, we can see that there is a 7 dB rise between 300 hertz and 2.7. So that's basically orthotelephonic response. That was about the transducers. Now, coming back to how will you put these transducers inside the housing? First, we wanted to see is what is the usability conditions. The rule of thumb here is that you wanted to place microphone and speaker in the opposite directions so that you can minimize the coupling. Coupling is the energy acoustically getting fed back into the microphone, and farther they are, smaller will be the coupling. And a smartwatch, you cannot really design a big watches. So you are limited by the diameter of the watch. The speaker size is limited by the thickness of the watch. So care must be taken. How do you place them? Do not place them on the same side. Otherwise, you will have a strong coupling. Rule of thumb is, in order to have a decent duplex performance, when you measure the microphone energy and then you measure the coupling energy, microphone signal without coupling will be at least 6 dB greater than the couple energy. That you can give. Echo canceller can take care of that echo, and you will have a decent duplex performance. On the other hand, if your echo coupling is stronger than your microphone signal, expect poor double talk performance. So these are some design challenges acoustic engineers to take into consideration, minimizing the coupling. So that's about transducers and acoustics. Now let's go into the auditory system. Human auditory system has three basic: the outer ear, the inner ear, and the middle ear. Inner ear and middle ear is connected by this. Inner ear and outer ear is connected by this middle ear. Outer ear acts as a receiver. The middle ear is basically a impedance matching device. Its main job is, this is a air, and these are three bones here, and its job is to act as an impedance matching device between the inner ear and this outside sound, and convert sound waves into vibrations. And that vibrations now, the middle ear, through these three bones here, they are written here, and they are attached to this 2.5 ton coil known as cochlea. Its base is sensitive to the high frequency, and apex is to the low frequency. If we stretch the cochlea, it's about 3 centimeters, and its structure is like, it has these hair cells, each sensitive to a particular frequency. And in terms of a signal processing, it acts like a spectrum analyzer, or each hair cells acts as a band pass filter. If we put these together, this basilar membrane, its frequency response looks like this. So we'll come back to this one when we will be talking about perceptual model, auditory model, or bandpass, or when we'll be designing basically a subband system. We will come back to that. Just to give a brief here. So our mind perceives sound not linearly, but logarithmically. And all this is doing here is basically at lower frequencies, you need a more loudness, but the frequencies are closer. At higher, you need less loudness and frequencies are spread out. This is the reference we have taken it from. Now, that's more on the Cochleae side. Why do we have 2 ears? What is their role? What is the function of the head? Our left ear acts as a left transducer. Right ear acts as a right transducer. However, it cannot tell whether the sound is coming the front or from the back. And for that, we need a head-related transfer function. So how mind knows where the sound is coming from? It uses these 3 cues, 2 binaural cues and 1 monaural cues. ITD, ILD. ITD stands for interaural time difference, means your left ear is listening, your right ear is listening. That's interaural time difference. How much is the minimum or just noticeable delay? It's 10 microseconds. And note that whenever you are designing an audio system, this 10 microsystem plays a significant role. So it could vary from 10 microsecond to 700 microsecond. ILD, the minimum that our mind can detect is 0.5 dB. Between left ear and the right ear, we could have up to 20 dB difference. Care must be taken when you are equalizing. Which ear you are using when you are doing a subjective testing and you only use your one ear, not the other ear. What happened there? So ILD depends on which ear you are using. For localizing sound, ILD is used below 1000 Hertz. ITD is used below 1000 Hertz and ILD above 3000. And between 1000 and 3000, it's a gray area. You have to use both, including head-related transfer function. We'll come back to this one when we will be discussing about spatial audio processing. Now, coming back to the dynamic range, we briefly described this one when we were talking about the amplifier. Human auditory system can hear 0 dB SPL sound all the way to 130 dB. However, 130 dB SPL is what we call a threshold of hearing. Means beyond that, you don't want to really play sound. Signal to noise ratio is determined by the floor noise and the full scale out. Floor noise is determined by where you are measuring a sound. If you are measuring it acoustically, you may be seeing a floor noise of 40 dB SPL. If you are measuring that inside the anechoic chamber, and the anechoic chamber floor noise is 10 dB and your electrical noise is 10 dB SPL, you cannot really characterize it whether this is electrical or this is due to the chamber. So you have to design acoustical chamber in such a way that it can characterize the true floor noise of the system. Dynamic range versus bit width. 16 bit width will provide you theoretically 96 dB dynamic range. 24 bit width will offer you 144 dB dynamic range, basically better floor noise and headroom. 32 bit width will provide you more headroom, better floor noise. So your dynamic range will be up to 192 dB. The typical in the background, acoustic background noise could vary from 30 dB to 55 dB, or could be 60 depending on if you are in a cafe environment. But typically is around office environment is around 40 dB. So 30 dB is a quiet environment like a bedroom, and 50 will be when you are outside walking, car passing by, that kind of a noise. So 50 dB, we can say that's floor noise. 90 dB is the headroom. So in terms of the SNR, in typical acoustic environment, 40 to 50 dB you need. Plus, with a noise gate or noise suppression, depending on the floor noise, it can go down to 20 dB. So total, it's about 70 dB of SNR system need to support. Auditory system, intelligibility versus bandwidth. This is straight from the literature. And if we plot frequency versus sound pressure level, this curve here is threshold of pain. This curve is a threshold of audibility, or we will be describing a little later as equal loudness. So this is the human auditory system, 20 kilohertz to 20K, what you can hear. For music, this curve represents music, 50 hertz to close to 16K. For voice, 150 hertz to around 6,700 hertz. That's where you can get most of the voice. That's in terms of the bandwidth. Now let's take a percentage intelligibility versus listening comfort. So this is on the x-axis, it is sound pressure level. On the y-axis, it's intelligibility. You can see from this graph, from 80 to 100, there is hardly any difference. So we don't buy much going from 80 dB to 100 dB, 20 dB, other than adding distortion. In terms of relative loudness versus the spectrum or the bins, more than 50% energy comes from less than 1000 hertz, below 1000 hertz. More than 80% intelligibility comes from over 1000 hertz. So you need both frequencies. You need low frequency for loudness. You need a higher frequency for clarity. We'll revisit on this one when we will be talking about DRC design, equalizer design. So that is about our auditory systems. So let's go back on the how do you model our cochlea? There are three models. First is a transmission line model, which is not realizable. It's expensive. It adds latency. And by the way, our mind processes signal every chunk of 10 milliseconds. And we'll come back to that, what that meant. So any processing we are doing need to be completed under 10 milliseconds. So transmission model does not offer us that flexibility, so we'll discard it here. Perceptual model is basically a widely used in machine learning. And we'll come back to that when we'll be talking about how sound is originated and how this is converted in the form of a machine learning pre-processing. Psychoacoustic model, widely used for acoustical signal processing. When we are directly optimizing audio for human hearing, we need to take psychoacoustic model into considerations. When we are designing a speech recognition system or any other machine learning based system where speech is being manipulated by the machine, we use this perceptual model. We'll come back a little later on that. So there are three key attributes of sound: pitch, loudness, and timbre. This is what our mind perceives. The physical characteristics of sounds are fundamental frequency, intensity, and the spectrum. The terms loudness, pitch, and timbre refer not to the physical characteristics of sound, but to the mental experiences that occurs in the minds of listeners. In the perceptual, as I mentioned earlier, our mind processes speech in non-linear fashion, or it's more like a logarithm, amplitude and as well as the pitch. So Mel scale is used as a perceptual scale based on how human perceives pitch, rather than on the physical property of the sound, like frequency, fundamental frequency. The mind doesn't really see that. And this logarithmic scale represents pitches judged by a listener to be equal distance from one another, which each pitch class doubles the frequency of its predecessor. And it is so basically, we will come back on this one when we will be designing the pre-processing for machine learning. For now, the Mel scale uses these filter bank. It's a triangular filter bank, and to convert, when we take a signal, we apply a short time Fourier transform, and that gives us a signal in a spectral domain that's still a linear. We need to convert signal into non-linear domain, and that's where this triangular filter will come into picture, and we will discuss this in the signal processing session. Psychoacoustic model, there are three key components. Psychoacoustic model: critical bandwidth, threshold of hearing, and mask. Critical bandwidth, these are experimentally generated. There are total 24 such subbands. For narrowband speech, we use 16 such subbands. For narrowband is basically between 3,300 hertz to 3,300 hertz. Wideband starts from 150 to 6,700 hertz, and super wideband starts from all the way down to 50 hertz to 1,600 hertz. So for super wideband, we need to use all the subbands. At lower frequency, they are very close, and the equivalent rectangular bandwidth, this is determined by this between f1 and f2, is given by this equation. And when we plug in it there at lower frequency, they are very, very narrow. And as we increase the frequency, they start spreading. That's the critical bandwidth. It's basically equal loudness curve. It shows the sensitivity of our hearing system. The equal loudness curve shows the sensitivity of our hearing system. This shows our mind does not treat all frequency equally. At lower frequency, we need filters are narrow. At higher frequency, we need a lesser gain, but the filter bandwidth is wider and wider. Here is a chart showing that at say 125 hertz, we need about 45 dB gain, whereas 1000 hertz, we only need a 7 dB gain. So this is important curve. When we apply a gain, a volume, these equal loudness curve has to be taken into consideration. Audiogram, which takes about 9 frequencies into considerations, and it basically generates the equal loudness curve of an individual's hearing. And that is what is used for personalizing audio experience. More about that a little later, but just to give the significance of this equal loudness curve. The next important auditory system attribute is a masking. Masking, the ear is simply a frequency analysis device. Going back to our Cochleae model, yes, it is a frequency analysis device, and that can approximate signal as a band pass filter in Bark scale. For human auditory system, the perception of sound is important. We do not perceive frequency. Instead, we perceive pitch. We do not perceive spectral shaping, modulation depth, or frequency modulation. Instead, we perceive the sharpness, fluctuation strength, or the ruggedness. In all hearing sensation, masking plays a significant role in both the frequency domain and time domain. The information received by our auditory system can be described most effectively in 3 dimensions: loudness, critical band rate, and the time. Masking can be differentiated into 2: simultaneous masking or frequency masking and non-simultaneous masking, or we call it temporal masking. So what is simultaneous masking? Simultaneous masking occurs when a sound is made inaudible by a noise or by an unwanted signal of the same duration as the original. For example, you are listening your favorite music and the truck passed by. With loud, it can completely mask your conversation or your audio experience. That's a basically auditory mask. In order to overcome with that, if we have a mechanism, somebody is passing by, we increase our volume to mask the noise. Here is an example. This particular tone is audible because it is slightly above this masking curve. Whereas this sound is farther apart, but it is not audible because it is beneath this masking curve. So masking is basically controlling the SNR of a system based on the ambient noise. Simple concept. In non-simultaneous masking or temporal masking, there are 2 types. One is called backward masking. Another one is called forward masking. And backward masking is characterized by this time constant. We need to apply when we are applying temporal masking or non-simultaneous masking occurs when sudden stimulus sound makes inaudible other sound that are present immediately or proceeding following stimulus. The masking which occurs as sound immediately preceding the masker is called a backward masking. And the masking which occurs sound immediately following the masker is called a forward masking. When you apply this backward mask, the time constant, by the way, this is a very important concept when you are applying a attack time and decay time. That's basically a representation of your backward and forward mask. Attack time, which usually is around 2 to 20 millisecond. Decay time, which is around 50 to 200 millisecond. For AGC, for compression, for any other gain adjustment, these time constants plays an important role. So you are putting these subbands together, and it's important to put these time constants there. That's about the auditory systems, how we perceive the sound, how the psychoacoustic system works. The next topic we are going to talk about is how do we originate the sound. When we start speaking, our lungs start pumping pseudo-random noise. When it comes through the glottis, it starts vibrating with its natural frequency. Initially, it generates a pseudo-random noise or transient, and then it starts vibrating with its natural frequency. When this modified periodic and aperiodic sound comes through our vocal tract model, it modifies its frequency. It's basically a filter, means it has a transfer function. There's nasal cavities, mouth cavities, all of our tongues, jaw, lips, everything acts as a filter. So in signal processing terminology, how can we really describe it? Lungs act as a pump, sending the air through the glottis. It generates the glottis pulses. Glottis pulses once comes through this transfer function, it generates the speech. And let's take an example here. So the speech waveform is glottis pulses convolved with the vocal tract filter. And what happens? The first part is basically it's a transient. When the glottis is not vibrating with its natural frequency, so it creates a transient, followed by this a tonal voice, and this is basically what pitch will represent. And then when you stop talking, then it gradually die down. So this is a voice part, this is unvoiced part. More on this later when we will be talking about the signal processing part. How do we use this to feed this information to the machine, and machine understands how this speech is. So basically when we will be designing algorithms, we'll be revisiting on this one. Right now, I'm just giving a basic concepts here. The next topic is instrumentation. 3GPP has this requirement called TS26.131.132. If you are using VoIP, it will be a different external 920. There are three approaches one will need. Waveform for acoustical and electrical characterizations, empirical techniques for analyzing voice quality empirically, and then the subjective technique. There is no technique that can really replace a human being. So under different constraints, if you have a properly trained ear, you can identify many issues. You will need a specialized instrumentation. For audio analyzer, you can use B&K, Rode & Schwartz, head acoustics, sound check. There are many manufacturers out there. I just give an example of head acoustics, provided it supports this standard. Simulator, again, different company makes different hats. This is most widely used. So B&K 5128 hats. Radio tester, Rode & Schwartz is choice of equipment provider for this. In terms of the sound chamber, sorry, there is one more for characterizing background noise. And acoustic own this is standard, so everybody use this is standard. It specifies in ETSI's TS 103.224 standard. And so that's one standard you will need to follow and what kind of instrumentation you will need. In terms of the lab, you can have, it's a sound chamber. You can have semi-anechoic chamber or full anechoic chamber, depending on the applications. Semi-anechoic chamber where other than the floor, you have acoustic panels all over. In full anechoic chamber, basically you have acoustic panels all over, and then on the floor you have a mesh. So depending again on your applications, you will be selecting what kind of a lowest frequency you need to match. You take that, go to your chamber providers, and they will design a system for you. With that, we have completed an overview of system basics, what you need to know. The next follow-up sessions will be on what kind of a signal processing we need, and then how you will design an acoustic system or a telephony system or a wearable system based on the set criteria. Thank you very much.